must be really used to hearing your participation because it just felt different, And well, that's a cool cupboard behind you. It looks like real wood. It's not what do you call it? When it's just like a veneer.
Well, I'm in my parents' house, and this is an old house. Like this has been here, so I'm assuming so.
Yeah, you do. I think it's probably maple, but which is it's easy to work with. But the thing is, you don't see that nowadays. When you buy stuff, it's all veneer. I mean, it's very pretty until the veneer gets a cut in it or a scratch. Then that particle board goes, here I am. Okay, I gotta remember, where are we?
We were just about to hit Bayes' theorem or Bayes' rule.
Bayes' rule. I think before I do that, I'll just try to pick up another sort of an interesting problem. 3B. I have 3BC. I don't know why it's. I think it's. I don't know. This is another example. I don't know whether it's B or C. Hold on. Well, where is it? Where is it? Three C. What I'm thinking about is 3C. And this has something to do with guessing on multiple choice problems. So there's what are the events here? So the person is taking a multiple choice exam. It's multiple choice and M choices. And of course, sometimes people don't know the answer, obviously, and they guess. So the information they give you is that the event that they know the answer, in the event they know the answer, has probability P. And of course, what's the probability they don't know the answer? Okay, this is just a continuity check to make sure everybody's with me. P, of course, is between 0 and 1. It's a probability. What is the complement then? We got 30 people. So just somebody's
minus P.
I know you.
I know. I shouldn't have said anything.
No, it's good. I just want to make sure.
Okay. Well, somebody put it in chat.
Okay. Good, Ernesto. Thank you. I just want to make sure, because there was a thing that happened. Okay, so 1 minus P, and the other conditional probability statement they give you is a probability of that they got it correct. So C stands for big C stands for got it correct. Given that they don't know the answer, K is for no, is, well, what does that have to mean? Well, let's see.
Like that just basically means that they guessed and happened to get it right.
Right, exactly. Yeah. So you guys, that's good. So what do you think what probability should we assign to that? So we got a multiple choice exam. We're looking at one problem. They have M choices. M could be 3, 2, or more, maybe 5. So if you have M choices, what's the chance, just by guessing, you're going to hit it right? Okay, suppose I have 3 answers, right? Yeah, 1 over M, Ernesto's done, right? If you have 3 answers, what if you have two possible choices? It's 50-50, right? So, you have to be, if you didn't know anything and you took a multiple choice test with just true false all the way down and you scored them all right, that would be really, really unusual. You'd be extremely lucky, okay? That it happens in the world, but not frequently. So this is 1 over M. This is a slightly complicated problem because what are they going to ask you? Think this is all your given material here. So we should probably change color. What are they going to ask us? What would be an interesting question? So look at what we have there. Catherine got it right too long. Thank you, Catherine. What are they going to ask us? What would be interesting? So the probability that you get it right, given that you don't know anything, is 1 over n. But if you're the person given the test, what would be more interesting than that?
The probability that they knew the answer given they got it correct.
That's it.
Okay.
That's it. I think it's sort
I had to think about that for a second.
Yeah, it's sort of a subtle thing, right? But isn't that kind of, if you're a teacher, what you're more interested in? You want to know the probability that they knew it, given that they got it correct. So, how do we approach something like this? I mean, this is the thing you want. Maybe you should start with what we want and see if we can figure that out. We can kind of unwind that using the definition of conditional probability and maybe some conditioning at some point. So let's go to work. Let's see what we need to do. So get out of the way. I don't know how much space I have before it shuts down on me, but probability of K, knowing it, given they got it correct as well. It's a definition of conditional probability. What is that definition? It's the probability of Kansas City winning the pennant. No, KC over the probability of C. Okay. And what to do about this? I don't know. I kind of drew it. I'm not sure my handwriting is sufficient for the day. But what to do about this stuff? So can you unwind the probability of KC on the top? I don't want to send it back to where it came from. I want to write it conditionally the other way. So what can we do about the numerator there? Well, let's see. Remember, KC, intersection of K and C is the same as C and K. So we could do what? You could, just looking at the top, we could write that as what? Probability of
K times the probability of C given K?
Okay, so if you look, okay, so this thing here, so if you look at the probability of C given K, that would be KC over K. So C given K, so it's probably a C given K times the probability of what?
K.
Times K. Why is that true? Because this is, so probability of K times C given K is K. Okay, so probability of KC is the probability of K times the probability of C given K. Okay, it's just a little substitution in our heads we got to make. But you can use the general product rule, right? This guy right here is the probability of K times the probability of C given K. I just wrote it in reverse here. You can just use if you don't want to do that arithmetic in your head, the algebra, whatever, you can just use the multiplication rule. Now here comes the hard part. What about the probability of C? I don't see that down here. So what do we need to do? We need to condition on what?
Right. I was actually just about to suggest that. Last week we talked about conditioning. So maybe probability of C given K plus the probability of C given not K. Okay, we got to be, I see. You're going to go, you're kind of deriving it. You're kind of deriving it, but actually, there's actually conditional formulas. Remember, if the things you're conditioning, I see. Probability of C given K times the probability of K. Very good. Actually, I just forgot that. Thank you. You were actually deriving. You were actually in the process of re-deriving it. Oh, cool. But yeah, then times the probability of C given not K times the probability of not K. Okay. So
I mean, there's a lot of stuff that just happened here. Let's go over the things that just happened, okay? Especially if you're confused about what's going on. This is the thing we're supposed to calculate, right? And all we did is write this, the definition of conditional probability. So that was sort of automatic. But from here, there's something, I want you to look at this real carefully. You have K given C here, see that? But when you work with this, you're able to go on the other side. It changes. It was this K given C, and now it's C given K. Why are we able to do that? Because the definition of conditional probability, it doesn't matter, you see, whether it's KC or CK here. It could go either way, and this is what the Bayes formula exploits. So that explains what's happening in the numerator. In the denominator, this was like the HIV problem or the medical problem we did, right? Where you condition to get P of plus, but here it's P of C, and you're conditioning on K here. Okay, so let me see if I have a question on there. Somebody said, "Is this?" So this is. I've taught this course before a couple of times, and the second time I said, "Look, this is mini Bayes." Bayes' rule is a little more, okay? Because if you look here, I need another color here to explain what I'm doing. Look at the K, okay? The K in here, the K complement. So K and K complement, they're disjoint, and their union covers everything, okay? The whole sample space, K and K complement. But there's no reason why you couldn't use 3. You couldn't condition on 3 different sets as long as they're exhaustive and mutually disjoint. That is the Bayes formula, okay? That's the Bayes formula. At least it's in Ross, okay? So in this case, the K and the K complement, those are exhaustive. That means that their union is a whole sample space. Okay, what's next? Well, we have to answer the question. So what is the answer to the question? Well, what is this? C given K. Did I make a mistake? I think I may have probably, okay. How am I going to get C given? Let me just check this. I've got C given K complement. Let me just check.
Well, wait, but okay. The probability they get it correct and they know it. Okay.
If they know it, they're
going to get it correct.
Should be a 1, because if you know it, then you're going to get it right. There's no noise in this problem. Okay, so thank you. Probably of K, this is a P, right? Of knowing it. Right, I just stopped. So what about this? This is a 1. This is a P, but what's this?
I thought it was going to be like, if they think they know it was K.
No,
we're trying to keep it simple.
Yeah, that would have made it more complicated.
They know it. So the probability of C, this is provided, this is 1 over N. And then probability of not knowing it is 1 minus P. So this is, I don't know, let's see, so what's the answer though? P over P plus 1 minus P over M. Sorry, I'm writing so small you probably can't see what I'm writing. Okay, so that's equal to what? MP over MP plus 1 minus P. I think that's correct. Yeah, I had a problem here because I wasn't thinking logically. If you know the answer, the probability of getting it correct is 100%. Sorry, I wasn't thinking. But thank you for making me aware of that. This is Bayes, not Bayes. We're not quite at Bayes. We're just keeping it at bay.
Well, if I can, we have a way to define P of not K, and that's 1 minus P. Or, well, basically we can substitute there. Should I keep going or no? I can stop.
No, keep going. So
Okay, so my thought process is I really want to factor out that P, the probability of K. So I want to substitute in 1 minus the probability of K for the probability of K complement.
yes,
Okay,
that's what we did, right?
effectively, yeah. But more just like in terms of writing it out for Bayes' theorem. Like I feel like that's something we could do.
Huh.
Or no. I don't know what the Bayes' theorem is like off the top of my head.
Well, let's do it. Let's do it because we have all the ingredients. I mean, we could just write it down now because it's the same. It's exactly what we have here, just a slightly more general. That you have you're conditioning on more than one set. So.
Okay. Never mind. Yeah.
But it should be there. I mean, I'm not saying it's easy because last time I was trying to explain the Bayes formula, I messed up. I think what was it? The law of total probability. I did something stupid. But let's just take what we have. Let's leave what we have here and see what we can do. So the most useful thing I've found in algorithms is this law of total probability. So the law of total probability, how does this one go? If you have a bunch of sets that are exhaustive, the union is everything, and they're disjoint. So let's call those sets F sub j. So these are exhaustive and disjoint. Then you can look at the union of E Fj. So in other words, how much of for each Fj, how much of Fj is in E? And the probability of this, I hope I get this right, is then what would be the sum of these probabilities because they're disjoint, these sets. Okay, but you can write this sum as, this is why I got messed up last time. So you can write this is the conditional kind of thing. So this is probability of F sub j given E times probability of so S this is E. Hold on, let's make sure I didn't blow that again. Nope, I blew it again. So hold on, sorry. Let's just write it. E given F, so no, you don't want to split it this way. We could write it this way, but I don't want, for this application, I don't want to do that. I want to go, what do I want to do here? E given Fi, and E given F sub j times the probability of F sub j. I want to write it this way. And the y is a little complicated. But this is the way you want to have it for the formula. So how does this, so this is the law of total probability. So, and again, I've done a mistake because I forgot to put the summation in here. Okay. You add up all these, but then you can split these like this. So how is that related to something above? Okay, so I'll use the green here again. So how is it related? Well, here you had K and K complement, see? And we multiplied by the probability of K complement. So if the sum only had two terms in it, it could have K and K complement. The F1 would be K and F2 would be K complement. So what's going on at the bottom is the rewrite you get from this formula. Okay, this is a little more general because you're splitting it over a lot of, you're conditioning over a lot of these sets. I'm sorry, I got it wrong the first time, but you're conditioning over these F sub J's. Let me check the chat. Maybe I've lost everybody. It's awfully quiet. Do you guys understand how this is a special case of this? Is that a legitimate question I could ask?
I do have a question.
Yes.
So why f of 0, and what is that f of 0 even
Where's
doing?
an F of 0? I didn't mean it. It's all J. This one here?
Yeah, what's that?
That's a J.
Oh, so it's all the f of j?
Yeah, yeah. So J goes between 1 and N or something here. Something like I'm suppressing I'm suppressing the subscript so that we can just see the structure of it.
But what is the probability of f of j? What does that represent though?
Here?
In that problem in general.
For what it's worth, in my notes, I drew a picture of a disjoint union.
Yeah, yeah, okay. Here's the whole sample space, right? So maybe I've got F sub 1, F sub 2, F sub 3.
Oh, so it counts just for all of them.
Yeah, it's going to go.
Oh, okay, but that's simple.
But actually, it's actually something not simple about it. You're trying to. You're basically, I think it's conditioning on all the F sub J's. So you've got all these F sub J's, and it's sort of splitting and say, well, how likely is E if F sub J occurred for each of these terms? We'll see. You know
So you could have like so in that diagram you just drew, like you could have like just draw a circle for E, right? That overlaps on some of them.
Yes.
I think that would be a good way to visualize it, maybe.
That is, yeah.
And so you figure the probability given those events, and so this only works for if the F's are all disjoint, right? Like none of the F's overlap, right?
Right, but you know what? Maybe I've been not a good teacher because I probably should have said this is the probability of E. You know, probably should have written that. So this is the probability of E. Because you're splitting E up into all these disjoints. Because the F of J's are disjoint, you're splitting up E into these different pieces. And they're exhaustive, so you catch all of E that way.
Ah, okay.
So I don't know what to say really. I mean, we know from examples that sometimes you have this conditional information, but you don't know this. And you have all the conditional information. But like, for instance, right here, right? So what were we given here? We were given this and this, right? It turned out this was one, this was easy. But we were given this conditional information. So that allowed us to figure out what the probability of getting it correct was.
Professor,
Okay.
I don't get the last step. Are you using the multiplication rule, or that's
Okay.
not the, because it would be the other way around if it was the multiplication rule. It would
Well,
be
hopefully I got it
F
right.
choose given
Let's
E.
check it out. So let's check it out. So we have P of E and F sub J, right? So we could do the multiplication either way, right? You could do it as a probability of F sub J times the probability of maybe hold on, maybe
Oh, I
right.
thought it was it would be probability of E times.
Let me check.
I don't know, based off of what it says in the book.
Exactly, yeah. So let me see if I even copy the right. So P of E is okay. This is what I get out of the book. So okay, so this is correct to this point. So why is it correct? So you want the probability of F sub J. Okay, so you could write it this way. You could start with, okay, maybe this is easier. If you write instead of E and F sub J, what if you go F sub J and E? Okay, what if you write, this is the same thing, right? Because intersection.
Wait, why are they the same thing again?
Oh, that's okay. So if you have two sets, this is A and this is B. This is AB, right? You can call that AB, you can call it BA. It B and A, it doesn't matter.
So it's because it's
So it's
exhaustive.
Another word is
There's
and.
reason?
Well, what it means is the event that E and F of J happens. It doesn't really matter which you say, E and F of J or F of J and E. So that's why it like you can change the order in terms of E and F and J versus F of J and E.
right.
It just means and.
Right. So that's that. Well, that's kind of the essence of this. Why they're able to do this magic, because there's two different ways of considering this conditionally, and it can either go towards the A or towards the B. So if you write this, right? Okay. So we're looking at this, right? If you write it this way, then you could use the multiplication rule as it stated. So it's a probability of S of J times the probability of E given S of J, right? So that's what's going on here. Does that make any sense?
It clarified it, but it just doesn't follow what you did in 3C with what you did now. Because in 3C, P of KC is not equal to P of CK, right?
Okay, that's a good question. So let's take a look. Let's try and find who's who
That's
here.
why I'm like,
It's up there. It's on the board. Where you have P of KC in the numerator. We're just trying to make it look exactly the same. Let's see here. No, well, I mean, I see it. I can point to it on my screen, but you can't see where I'm pointing.
No,
No,
okay,
the numerator. In the numerator.
This?
Yes, it's to the left. We're trying to make it look just the same. From there to there.
Oh, okay. So this is the probability of. You could think of this as the probability of C. The probability of K times the probability of C given K. So it's just been written that way, but it could be, if you want to use the multiplication rule, I think I'm out of space here, but I don't know, maybe I get lucky and I can write it. So you want to use, I'm not sure if this is the question, but you want to be able to write that, right? Or be able to see it.
You can see it well enough.
I'm sort of out of space. So why is that? I'm not even sure that's your question, but we're looking at this and we're looking at this, okay? So you can think of this as the probability of K, using the multiplication rule, times the probability of C given K.
so my question is, why isn't the first one, why isn't P of CK equal to P of KC? That's my question. Because in the second one, I see that, there's a union. I guess you said because it's exhaustive. And so there's a union. And so you know that there's going to be, like, it doesn't matter if it's A or B or B or A because it's exhaustive. But I don't know if that's the same, if that applies for the first question as well.
What I think's happening, I suspect something. It's just about when you go the definition conditional. So let me try this, okay? What do you think, Aim? Is this a question?
What I'm worried about is, Elizabeth, are you talking about probability of K given C, or are you talking about probability of K and C?
I think K and C. Yeah.
Okay, because that's the one where there's no line between them. So, I mean, the only other thing that I would do is I'd rewrite it like from the other perspective. So what I would write as well, just to show that they're literally the same thing, is probability of C times the probability of K given C, like right on top of it, just to show that they literally, like, they are equivalent.
Okay, let's make sure I got the right thing. So we're looking at these two expressions.
There's another, my point is just that there's another way to write probability of KC, and that's from the other perspective. Probability of C times, okay, cool.
Let's do it. Let's try to do it. So, okay, I think what she's saying, Elizabeth is saying that we know the multiplication rule, right? How does that go? Probability of K times probability of C given K, right? We're good with that, right? That's the multiplication rule. Probability of K times the probability of C given K. Are we good? You're good with that, right?
Mm-hmm.
But what if you do it if you write this the other way? It's the same thing. These are the same thing. But what would the multiplication rule say now?
Let's see. A given C. Yeah.
So you get a different looking thing from the same thing. It depends on whether you're gonna write it. When you're looking for probably a C given K or probably a K given C, you can get them both out of this. It's just different. It's different, but this expression is the same as this.
It just depends on what information you have.
All right. I wasn't sure. Thank you. That helps.
Which direction you want to go, it depends on the data that's been supplied. Right, exactly. But this is sort of the fact that you can write it both ways. That's the essence of the Bayes formula. Okay, that's what they're doing. So let's see if I can get the Bayes formula down here.
So Bayes is just a generalized form of that mini Bay that you showed us.
Exactly what went on here, and the HIV problem, or the other one with the A.
Instead of like binary logic, you can apply it to any number of alternatives, huh?
Hello. Okay. Yeah. So let's try to get the general formula. This is okay. So this should apply to any situation. This is the max for this. So let's what is the purpose of Bayes formula? So you want to know the likelihood of some event occurring given that E has happened. How likely, given that E happens, how likely is it that it occurred? So the event we can look at is F sub j. So the probability of F sub j given E. So we know that E happened, and we want to know about this. We have different Fs there. They're exhaustive and disjoint. But this is, we really want to know if E happened, how likely is it this other event happened. So let's see what we can do here. So the first thing is to go with the definition. So what is the definition? Probability of F sub j and E over the probability of E. Okay, there's no problem with that. But we can do the switcheroo on this one here. So we can think of this as what? So probability of, we can use the multiplication rule, probability of F sub j times the probability of E given F sub j. Now notice how it's the conditional thing has switched in the top. Oh, I should give the name of this. So this is the Bayes formula. Okay, so we did that. So that's what we've been talking about. But the thing is, now I want to expand out this. So I want a condition on all of those sets F sub I. So how does this work? How does it work? Let me just make sure I got it. So I want a condition on all of this. So okay, so probability of E. So probability of E given F sub j times the probability of F sub j. So I'm conditioning E on all those sets. So just for your notes' sake, so F sub j is exhaustive, just like the lecture. No, exhaustive, and they're disjoint. And mutually exclusive is the fancy way to say that, but I don't have space to write that down. You can impress your family and friends with that speech. This is the final formula, okay? The Bayes formula. So how is it related to the thing up here? Well, you started with K given C, and you ended up with C given K. So here I started with F sub j given E, and now I'm going E given F sub j. So that clicks with the numerator. And the denominator, instead of having J of these things, you only had two. You had K and K complement. And let's just make sure that it did what it's supposed to have done. So So K was F sub J. So E given F sub J. So let's see. So down here you had E given F sub J. So this is what's happening with this. Okay, it's just a substitution. So this what we utilize up here was a special case of this. We only have F's 1 and F sub 2. Okay, let me check the chat. Yes, it's E. So, or make up. So you're adding all the.
That was from a lot earlier.
Okay.
Yeah, I figured it out.
So the way to look at this, and I'm not a good role model for this, because I don't use this formula. But if you're going into statistics, actuary, something like that, when you have a conditional probability issue, you want to apply their theory. That you just go to the formula. Don't bother with trying to derive it again. If you're going to be get a master's in statistics, then maybe you'd say, okay, how do I derive it? Well, the top is just the definition. The bottom is what? What is that called when you take this into this? What was that called? P of E. You conditioned E. Conditioned on all these F sub J's. That's the law of total probability. What makes it total? Here's the question, just to make sure you're following. Why would they say total probability? Why not just law of probability? Where does the total come in?
Okay.
They're exhaustive for
Yes.
E
Yes.
or for the entire sample space. I'm not sure. But for E, right?
No, for the whole sample space. So
Oh, okay.
the total list, it totally covers the F sub the J's totally cover the
The sample space.
yes.
Okay.
So you're summing all the little pieces of F, right?
You're conditioning. This is called conditioning on these others. Usually, it's conditioned on one set. Like A and A complement. Here, you've got a whole lot of them, and we derived it just a second on the law of total probability. That's what this is. So, but I think your question more is
You're summing.
what's the purpose? What's the purpose? You know that E happened. You want to know how likely is it these other events happen. Okay, go ahead, Ethan.
That summation on the bottom, you could think of it as it's summing up all of the different parts of E, where each part represents a different it's the what am I trying to say? You sum up all the different probabilities of E given that F.
Right.
Well, that's kind of restating what we're looking at.
It's
But
okay. Look at this. Some people call this a weighted average down here, where the weights are the likelihood of the different F sub J's. But maybe we should do a problem now that uses this formula as it is. For like 3 sets to try to see exactly what it's doing. Okay, should we do that? So, in other words,
I thought of a way to phrase it. It's like summing up all the different parts of E that correspond to each F. Because instead of, you're not just summing up all the F's, because those all sum up just to 1, but you're summing up all the
thing is,
all the E's.
you understand it's an average, right? It's a weighted average. You know what a weighted average is, right?
Yeah.
So these are the weights. These are the weights. So, in other words, if F sub J is a big, huge set, then you have to take that into account. Let's do the problem, because in Ross, he tries to make some sense out of this. But we can erase this special case up here. I can't touch this because I need to apply it. Okay, so this is a sort of an amazing problem. This is 3L. So we're going to example 3L. And this again is a sort of paradoxical kind of situation. So you have 3 cards. You've got 3 cards. So what do they look like? This is not a full deck, believe me. So it's 3 cards. And only 3. So there's not much to shuffle when you want to play this game. It's not much to shuffle. Okay, so this one has red on the front and red on the back. This one has black on the front and black on the back. And this one, say, it's both red and black. So it's got red on one side and it's got black on the other side. And of course, my drawing is not very good. It's fine, okay? 3 cards. Now, if you only have 3 cards, you don't shuffle because that's real gambling, if you do that, that just shuffle, shuffle hustle. So instead, you put them in a hat and you not looking and you just pull out one randomly. So the thing you want to calculate is you lay it down, you pull out one of these cards and you lay it down and you see that it's red, okay? So what you want is, what is the probability that the other side is black? And this is a given that you see the up face. I should have said up face. Everybody understands what up face is, right? And the up face is red. Okay, now let's just step back for a second. This is a lot of verbiage here and a lot of writing that I don't write because I feel it just gets in the way. But you're going to take one of these cards at random, right? And you're going to lay it down on a table. So you're looking at the up face. That's what's staring at you, okay? And you see that it's red. I guess I should have drawn that in red, right? Should have drawn it in red. You're looking at this, and it's red. So they're asking you, what is the probability that the other side is black? Okay, now, most people, including myself, when I see this problem like this, I would think it's 50-50 because, we've either got the red card or the red card or the red-black card. I'm seeing red, so, 50% of the time it's going to be black, 50% of the time the other side's going to be red. Does that sit well with anybody? I mean, does that sound like a reaction you might have?
Yeah, that is my first reaction is, okay, well, I know that there are 2 cards with red on one side. So then it's either red on the other side or it's black. And there should be an equally likely chance of that. Well, I guess let's find out.
Yeah, but I want to, the whole point is of this thing is to somehow, I don't know, instill some sort of resistance to intuition.
Sure.
Okay? That's the point of it, right? So I hope everybody understands the problem. I'm worried that maybe they don't.
I was organizing my notes, so I kind of zoned out for a sec. Sorry.
That's okay. So you have 3 cards. This one's a red card. This one's a black. This is a red. You throw them in a hat. You take one of them out at random, and you slap it down on the table, and you look at the up face. You don't know what's on the bottom. And if the up face is showing red, what is the probability that the other side is black? And you look at what you have. You certainly can't be in this situation. It's either you got your red-black card or you got your red card. 50% is presumed to be the answer. Okay, so I'll just stop there for a half second.
Okay.
You're good with that? Okay, so somehow we have to utilize this formula on the bottom to do the problem. Okay, we're going to use the full power of this Bayes formula. Okay, so let's see. I don't really. What I really want to do is to do it for 3 cases. So what would be 3 cases here that we could split this in? We want to know. So the hard thing here is to is to get the events. Okay. So really, when you say the other side is black, you're talking about the probability of what? Then what card do you have there? You've got the red-black card, right? You know, that's a way of summarizing the fact the other side is black. If it's black, you got to have the red-black card. So it's what's the chance you got the red-black card given the up face is red? Gosh, I'm really in a situation where I'm not sure the space-wise I'm going to be able to do this. So let's just call this event that you see the up face is red. We'll just call that red. That's what you see. Okay. So we can rewrite all that. Hopefully, with I don't know. I'm in a bad situation. So you really want probably that you got the red-black card, given that you're looking at a red up face. So how could we apply this formula here? What does it say to do? I'll erase this so we get some little bit of space. It would help. What is this formula saying, telling us to do here? Is it this? This is what I'm looking at here. So it says that it would be the probability of what are the two events here? So I'm trying to make a direct appeal to this formula. So this was fill in as the F sub j. What are the F's here? And the three events are what? Well, there's three different cards: red, black, 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 red, red. So that's that, and then the E is this. So if we fill in for the formula, what is it telling us to do? It's saying, okay, what's going to be in the numerator here? Yeah.
So probability of red black times probability of R given red black.
Okay, you're doing. What am I going to do here? I'm doing the numerator, right? So probability of red black, yeah. So you understand what I'm doing. This is not the numerator. So this is the left-hand side here. So this is awfully messed up. So it's the probability of red black. That's the card you have times the probability of what?
Times the probability of getting a red side.
Given that it is the red black.
Given, yeah.
Yeah, this is just. I don't like the way I wrote this. It's just visually really hard to. I guess it will make more sense if we put the denominator into this. So how does the denominator go? So what are the three sets we're talking about? So this would be, I'm trying to do this lower part here. So probability of red, given we have the red-black card, times the probability of the red-black card, plus what? The probability of getting a red, given we have, what's another card? Okay, you'll get three cards. How about the black-black card? Times the probability of getting the black-black card. Plus the probability of red, given, what's the only other possibility?
The red card.
Oh, right. Probably good. The probability of getting a red. Just to make sure I have to be very careful that I don't make a mistake of some sort. So we're doing the probability of red. So it's all E's. E is getting that red. So probably
Professor?
Yeah, hold on, because I'm almost about to lose my where I am here. So probably okay. This is seeing a red given the red card times the probability of getting the red card. Sorry. All right. Okay. Go ahead and ask your question.
You answered it.
Oh, I didn't say anything.
No, you because I was so we're getting the probability of all three, correct?
Well, there's three. This involves three cases. It depends on, so F sub j is the card that you have. So there's three different cards possible.
Yes.
So right, so this is just like the formula. It splits into three pieces down here. The numerator, I think you guys are good with, right? It reverses it. Black given red, and now you have it expressed in red given red black. See, so that's okay, right?
Yeah.
So I don't know how to separate these. These are separate. Okay. Now let's see if we get 50%. So help me out. So what is the probability of drawing the red black card here? Remember, you took a card at random out of the hat and slapped it down. What's the chance of getting that particular card?
1/3.
1/3, right? Because you got three cards. That's not an issue. That's 1/3. What's the chance that it's going to show you a red, given that it is the red black card? So remember, it's cards taken out at random and slapped down. What's the chance you're looking at a red, given that it is the red black card?
50%.
Right. I'll slow down here and take a drink of water. So somebody, make sure everybody's on board with that. Okay? Some of these people get confused because they're thinking about the whole problem. But this is just, okay, remember, you choose a card at random, right? It could be any one of those three cards. You plop it down. That's what it could be the black card.
Sorry, so for the first part, it's 1/3, and then for the second one, it's 1/2.
Yes. Does that look? I guess it doesn't look like I have. Sorry.
I'm just wondering because I know that it's a different situation, but it's the same variable, if that makes sense, and it has like a different number assigned to it.
Oh no. The whole thing, that probability. Sorry. The probability is 1/2. So
Okay, yeah.
I'm sorry. I don't know how
That
to
makes sense.
Yeah. I'm sorry. I don't know how to do this. Where do I put in the numbers? You see, I'm not sure I can.
Could put them on a new line, like
It all has to fit. You know, it all has to fit. So the probability to get red is a red black card. It's 1/2. I don't know. Yeah, it's not. It's not. Those are events. Those are sets, but the probability should be 1/2.
Perfect. Thank you.
Now, what about let's just follow the formula down here. So what's the probability that I get a red given it's a red black card? So the red black card is the one that's going to go down, but what's the chance it goes face up red?
1/2 again.
Yeah. And what's the probability of pulling the red black card? Because there's only three cards. Now here's the interesting thing. What's the probability of showing a red given you pulled the black card?
0.
0. The probability of pulling the black card is 1/3. What's the probability of pulling a red given that you when I say pulling a red, that
You flip it over and it's
no, that you see that E is what you see, right? You see a red, so
so just red is face up.
yeah, that's what it is. It's face up, right? So given that this would be 1, and this is 1/3. Yeah, no. So these probabilities. So again, what were we trying to figure out? I've forgotten. What's the chance that if you see a red, well, that's event E, right? That E, given that you see, what's the chance that the other side is black? But the other side being black only happens if you have the red black card, right? Because you see the red face of it, and the back side's black. That's the only case. Over here, it doesn't happen with any. It's only this one. Wow, this has been a long, hard haul. So tell me what the answer is. What's in the top? What's in the top?
1/6.
Yes. Did you follow that, Abe, or did I totally?
Yeah, well, I mean, I'm also kind of doing it on my own. But that's not 1/2. So that's interesting.
Well, what is it exactly?
It's 1/3.
Well, we can round that up to 1/2, right? I mean,
No.
1 over 1 plus 2. Yeah, that is otherwise known as 1/3. What's going on here?
So is it more just like this is the correct way and it's showing that our intuition is wrong?
I
But
think it has to. Yeah.
I guess where I'm confused is it feels like if you look at it from the perspective of just reducing the sample space, you see a red card, so you know it's either the red or the red black card. It feels like it should be 50-50.
Yes, yes.
Yeah.
But it's not.
I
From
think
looking
I
at it
know
from
why.
baseball.
Sort of, but I.
But wait, before you say that, Ethan, let's see if
Uh-huh.
anybody else has trouble with these numbers, because
It's
somebody
really
could argue
weird,
we got
though.
the wrong numbers. Are you guys good with these numbers?
I'm good with the numbers. Like I see where that's coming from.
Question. So just
Yes.
so we're clear, this is the probability of red being face up, or red and black.
No, this is the probability of, okay, a card got slapped down, right?
Yeah.
This is the probability that given that when they slapped it down, you see an up face of red, that the other side, the hidden side, is black. See this right here? It's the
Okay.
probability that it's the red. So that means the only way you're going to get a black card on the bottom, a black face, sorry, is if you have the red-black card. Because the red-black card will show red on one side and black on the other. So what we want to calculate is what's the probability that you have on the table the red-black card, given that you see the up face being red.
Okay.
It's a little complicated. So the reason AIM is pointing out this seems paradoxical is because if you see a red face, right, then it can't be the black card, right? So it's either the red card or the red black card. So it's either one thing or the other. It should be 50-50.
Okay, I just had like a moment of realization.
That word. That's called an epiphany.
Yeah.
That's what people say it's an epiphany. It's an epiphany. No, but that's I love rap music. I never heard one where they use the word epiphany. they shorten it, epiphany. Okay, go ahead. What's the epiphany?
I accidentally clicked the wrong button. Okay. So intuitively, like Ames said, you want to reduce the sample space, and then you're like, so there's only 10 cards left, and 5 and 5, so it's 50-50. But I think what happens actually, as soon as you see it, that actually changes the problem kind of, because what we're seeing is only 1/2 of the thing that's there.
Yes.
So it actually kind of changes the weights. And so what you should actually consider, and so this is kind of mind-boggling, but I think I figured it out. What you should actually consider is the number of red sides more so than the number of cards that have red.
Okay, I think you may be right, because
It's like,
you've got 3 red sides. Okay, let's. Okay, so I remember when I first taught the course, the first day we talked about sample space, or maybe that was the second day or something. We had to figure out exactly what this experiment is. Okay, what is the sample space? In other words, what could happen? So, I think Ethan, you're close to the.
What Ethan just said helped me out a lot. And then I was going to do exactly what you just said, which is write out a table, write the actual sample space.
Right.
And whenever you do that, you reduce it down to where everything either is the same probability or you can see the probabilities. So, yeah. Anyway, what you're going to do is exactly what I would do.
I'm going to try to do it. But for some reason, I've mentally slowed down today, so I'm not sure I'm going to do it.
We've all had those days. It's okay.
It's the first class I teach. It's not it's like the first class I'm teaching algorithms, and it's very subtle stuff. It's not formulaic. You know what I mean? It's not formulaic. It's you're trying to imagine a whole sequence of moves or something that's optimal. I don't know. It's just different. It's a different kind of thinking. I think it's deathly to some people. Okay, what's the sample space?
this kind of problem like really tripped me up when I had that that other math class, there were like these two geniuses in the class, and then I was like, I could understand things pretty well, but there's this guy who was talking to me. He just brought up a problem for fun that was kind of like this, and he's like, okay, so now you've seen what's behind one door, and do you go with the other one? It's one of those things. And
we're not. No, I don't want to do the Monty Hall problem right now. It's gonna do the whole thing.
The point is, it freaked me out. I could not understand it. It went completely against my intuition, and I thought he was just not explaining the problem right.
Well,
now I see. I just didn't understand it.
What's our time? 12:50. Whoa! Wait. What's our story? We got time. I'll have to tell you how everybody's been humbled by the Monty Hall problem. I mean,
everything I know is wrong.
What is the sample space here? One card was selected, right? So basically, how many different things could happen? So you could have, if it's the red card, you could be looking at one face of it, or you could be looking at the other face of the red card, right? This is okay. So here's the red card, right? So you could be looking at one face of it or the other face of it. What about the black card? You could be looking at one face of it or the other. Okay? Well, or it could be the other card. So it could be the black card, and you're looking at the red face of it, or it could be the black card, and you're looking at the black face of it. So these are really all of the possibilities. They're all equally likely. So in other words, you took a card out of that hat and you slapped it down, you're in one of these situations. So I guess I should specify that you're looking, in this case, you're looking at this one, this one, this one. This is what's showing face up. So those events are all equally likely, but which of those correspond to seeing a red face? Which ones?
There's 3 of them in that case.
Yeah, you would see one face here. You definitely would see one here. And let's see, which one are we showing? We're showing, what did I say here? We're showing red, right?
Mm-hmm. Right, that one where red is on top. And so now it's really clear that there's actually only a 1/3 chance that it's the red and black.
Well, this is the red. We know it's this, or this with equal likelihood. Why do you know it's equal likelihood? Because the whole thing is they're equally likely.
That's how we set it up.
Right. So this is equal likelihood. So this is your reduced sample space. So amongst that, which ones correspond to having a black card in the back? So reduced sample space.
I'm following the logic, but I'm sorry, I can't understand your notation right now.
Oh, okay. Every card has 2 faces, right? So I'm thinking of the red card, but the one means we're looking at one of the sides, one of the faces of it.
Oh, okay. So the subscript is which side we're looking at.
Yeah. It's kind of a crappy notation, but it's the best I can do. So here's the red, the same card, but we're looking at the other side of it. And over here, you're looking at the red-black card, but you're looking at the red side of it.
Okay.
So these are all equally likely, but I just want to know which of these events correspond to, which of these outcomes equally likely correspond to what happened in the problem, because you saw a red card right on top. So it's this, or this, but only one of these is the reverse card and black card.
Cool. So this is like what I was saying, where the faces matter, but now I can actually see how that matters, like how to set it up.
Well, I don't know. I'm worried myself, and just my own understanding, because I'm thinking I don't want to think about these things. I just want to apply a formula. Like in calculus, you have various integration formulas. You just do it. And actually, one of the goals of math is to just know when to use a tool, and just pop it out. And I think popping it out was but
we need to trust the theorem first. So this helps us trust the theorem.
Well, that's the problem when you go to the Monty Hall thing. You're on your own,
You don't trust
Okay,
anything.
yeah, sure. Yeah, that's fair. Monty Hall is like an application. But this is nice because it's something where we could check it both ways.
Right. Okay. I guess that way. Well, you did it by a formula, which we assume that the formula is correct, and then we do the exercise. I don't know. I feel like I wasn't going to do this, but maybe I should mention the Monty Hall theorem to you, or a problem. I don't know. Does anybody?
Well, we have 10 minutes. So if that's all we're going to do, then sure.
Yeah, I feel bad about it. Maybe I better.
It might just confuse people. It might just confuse people. It's one of those.
Well, it's extremely humbling. And I remember when I was a lot younger, I used to go jogging in the Santa Monica Mountains. And I met a guy an old guy, he was a retired guy. He was a old country lawyer from the South. And he found out, I mean, we would chat, and he found out, he said, oh, you're a mathematician, you got a PhD in mathematics. So anyhow, he told me the Monty Hall problem. As I was jogging, I stopped to talk to him. And he said, do you think it matters whether you switch or not? And I said, no, I don't think so. And I'm jogging away. And, he had a courtroom voice, right? So I got about 30 seconds away, and I heard in the distance, John, did you say you had a PhD?
Oh my gosh.
You never mess with a country lawyer. Let me tell you, lawyers, they're always right. I mean, they're just smarter than us, so smarter than me anyhow. Boy, that was humbling. That was wasn't good. It was not a good day.
I can imagine.
He actually, he probably was in his 80s, and he did this hike every day of his life, 365 days a year. So I had discovered that there was a fire up there, and I discovered he actually did the hike when there was a fire.
Dedication.
Yeah. Well, there's a guy who did. I don't know. Is anybody a hiker out there in the class? I don't know. Have you done Mount Baldy, Mount San Antonio? There's a guy that did it 1,200 or 2,000 times, and unfortunately, he passed away doing one of them. He fell off the peak. But people get into these ruts where every day they do the same hike. It's something about aging or something like that. I don't know.
Well, it's meditative. Hiking in nature. It's supposed to be good for stress management and stuff. That's irrelevant.
No. But then you take it like have you done the Cactus to Clouds hike, the C2C? That's not, there's no turning back. I mean, it's like if you turn back, you might die. so people have died, So there's an edge, right? There's a line, between meditative and now this is rolling the dice.
Survival.
Look it up, Cactus to Clouds. Cactus to Clouds. Okay, let me do another problem. Okay, so independence. The trivia thing. The town of Independence is known for what? Historically, I'm really seeing if you guys know your trivia. Independence, that was the state capital for a while because it was right in the middle of California. But for independent events, so you say that A and B are independent if and only if the probability of AB is the probability of A times the probability of B. Now, the story doesn't quite end there, okay? But I think, we have limited time. Let me check. We got 5 minutes. Let's play around with this just a little bit, okay? What does it mean intuitively for two events to be independent? It means that knowledge of one of them happening does not affect the chances or the odds of the other happening. So you might say, well, that's the way life is, right? If something happens in Florida, then it has nothing to do with some small event that happened that's going to happen or in Eastern Africa or something like that, right? Do you know what the butterfly effect is? Anyhow, it turns out that a lot of events, things that happen in nature are actually not independent. Like sunspot activity with agricultural productivity. Okay, you would think the sun is whatever it does, and whatever the farmer grows and success growing has nothing to do with each other. But that's not true. But mathematically, if what it means is this: if you look at the probability of A given B. What do we know that is? Well, we have a formula for this, right? Probability of AB over probability of B. If these events are independent, according to this formula, what do we know the numerator is? If there is A and B are independent, what do we know? The probability of AB is probability of A times the probability of B. So those cancel out. So if you believe in this formula, if you think your sets are independent, your events, then the probability of A given B is equal to what?
Probability of A.
So that means that knowing that B happened does not affect whether A happened or not. Now, I'm in a weird position here teaching the course because I don't go with the take-home test, right? The take-home format. So I have to, one of the few places I can go to escape Chegg, the Chegg demon, is problems of this sort. Like, let me give you a trivial example, a relatively simple example, okay? So this is the kind of thing that I would put on the next test. Suppose you know that A and B are independent. Then you want to prove that A and B complement are independent. This is like a little bit of proofy stuff here, but it allows me to manufacture questions that may not be so easily done by the Chegg tutors. And plus, if you remember this problem I keep on mentioning, 3.66, and with the circuit diagram, you've got to be thinking about along these lines, okay, to be able to do that in finite time. How would you prove something like this? How would you prove it?
Can you draw the Venn diagram of what A and B complement? So it would be A and then not B or something?
Yes, okay, you're starting to prove
Like
it.
Yeah, I mean, the only way to actually to understand it is to visualize it, I guess.
Well, first of all,
Using-
if we're gonna prove
the first step.
The first step, right? But what was the final step? We want to do what? If we're going to show, what would be our final? The probability of A and B complement. What are we trying to make this equal to? What do we need? What do we need? We're kind of trying
To be A, right?
say again.
Probability of A times the probability of B complement.
Right. Let's stop there for a second. Right, because that would do it. If you can split them like that, that would do it. But what makes us think we can do that?
Base theorem?
Actually, I need to give Elizabeth credit here for a second because I need to do what she said. I need to do what she said because this is A and this is B. What is A B complement? A and B complement.
Yeah, that side.
So okay, I was wrong. She was right. So this is what's on the left side. So we can see that as what? You can see that as so A and B complement. How can we can see this as a split of A? So A B complement. I'll be done in a second. So A B complement plus union what? Union what? This is union AB is what?
That's A.
That's all of A, right? So you have over here AB complement. So, but these guys are what? AB complement and AB are what? What kind of sets are they?
They're disjoint.
They're disjoint. So you can do what? You can write AB. So that means that the probability of this guy, which is what I have, would be the probability of A minus the probability of AB. Okay? I'm sorry, it's going quickly. So I need to put that in here in a hurry. So probability of A minus probability of AB. Now I can use the hypothesis that A and B are independent. I can write this as P of A minus P of A times P of B. Okay, but I can write that as I can factor out P of A times 1 minus P of B. And guess what that is? What's this? Did I erase? What am I supposed to, P of, no,
Oh, it's right there. Yeah, we're good. 1 minus P of B is B complement.
good. We can play this game on the next test. And what's shocking to me is that Ross, he's missed one of these. There's a classic one of these, and he missed it. And it was a perfect problem. It's a perfect problem, but it's a perfect problem for the midterm.
I'm expecting we'll see it. Most likely.
Yeah. I mean,
Okay.
Sometimes it's amazing. You look at a textbook and what problems do they include and which ones do they exclude. And I think it's just, you can't be perfect. And his book's almost perfect, but he's missing one problem, at least in my opinion, of this nature.
For sure.
All right. Well, that was good. We'll pick it up on Tuesday. I have a committee work deadline on March 1st, so I don't think I'll be able to start grading your exams, nor can I give you the next exam right away. So it's up to you guys to read it.
It's not done already? You don't have the test ready for us?
I haven't. I just look. All I did is look. I told you what happened, right? Maybe I didn't. I congratulate everybody that nobody checked, right? And then guess what? I went to check and said, "Hey, that's one of my problems." And somebody said, "No,
One thing. Well, okay, we didn't pay anyone, but just out of curiosity, we did Google one thing and we found it and we could prove it was wrong. So that's nice. We could actually find a counterexample to say, okay, clearly that's not the correct answer if you just Google it. So just wanted to throw that out there.
Yeah, I'm just sort of bemused because I had been checking all the way up until the deadline and nobody checked. And then finally, literally hours before the test, somebody checked. Maybe they were just checking if they got it right. But I suspect it was a group situation. And one guy was responsible for something he hadn't done it yet. Or it could have been one of the solo people who never shows up to class. And they have somebody taking the class for him.
Okay. Well, I mean, there's a difference between, putting a forum post out there, like somebody from the class actually going and asking. Maybe that happened. Our group certainly didn't do it.
Yeah,
but we were just Googling to see if someone had asked it sometime in the past and we found it, and it was wrong.
Wow.
So
the Czech tutors failed you or something. Failed somebody. But on the overall though, I mean, that's still a victory. Because when last semester I gave a problem in the higher class that I teach, and somebody checked it within 15 minutes. So I don't think that would have been enough time to read the problem and understand it before they checked it. And other people were crazy. The class went crazy because they knew, we have a thing going, where come to me first before you check it. I'll give you a hint or something, It was in groups. It was
just answering the previous question.
Yeah. How would they not know? How would you not know?
Hopefully they would know.
Have we ever discussed people working in groups? I don't know. I thought we did. Group size is as big as 8. You can have eight souls in it. All right. Well, look, I'm sorry.
What if one soul is not equal to another, though?
Okay, I'm going to head out then. I don't want to deal with that.
Aim, I'm glad your mic's working again.
Yeah, me too. That was very frustrating. But yeah. And just one big thing about this is aside from high school statistics and taking 341, this is my first time looking at a lot of these things. So don't think I know all the things. I'm still learning it like everybody else. I've just maybe I've taken combinatorics and I've taken 341 and so maybe I've seen a little bit of this before, but I haven't seen everything. So, I am still genuinely taking the course.
Good.
Yeah, I have a huge advantage. I almost said disadvantage. I have a huge advantage from having taken combinatorics as well. So,
yes,
big help.
And Elizabeth, you were right about this. I don't know if you're still out there. You were right about doing this.
I was just watching YouTube videos about how drawing the geometry of if you're stuck, just making it visual. It helps with your first step.
Yes.
Because it's all just ratios and for probability. It's all just
I've Googled numerous times trying to understand visually independence, and I've never been able to get it. I've never been able to understand.
Weird. Like, because, well, the intuition that I always see whenever you bring it up is independence means equally likely. But that's not what that means. It does not mean equally likely. It just means that it doesn't depend on something else. So, yeah, you want to avoid the intuition going into the wrong thing. Anyway, that's where I'm at with that.
I wish there was one. I wish there was a way to visualize independence that I could understand. I mean, it's whenever I look at the pictures they draw, they're like I just have a hard time. I just don't quite. I know they have colors and shapes and rectangles divided up into sub-rectangles, stuff like this with the events. But I just don't. It seems like it's more work to make that picture than it would be. Just the little,
Right.
It's like I don't know. It's a slippery concept.
It is. It absolutely is. Okay. So do you have an idea of when we're going to just start thinking about the next exam? Just in general, it's on the syllabus. Yeah, that's true.
Well, no, actually, no, because I got hit with this committee work.
Oh dear.
My desire is to give the test to you as soon as possible because it functions also as homework.
Right, it does. It absolutely does. And, and I really like having the time to think about it and play around with it and look through the textbook.
I just can't see doing it this weekend because of the deadline, the March 1st.
Totally fair. Yeah.
But ideally, I would give it to you. And this is I forget, does the test have chapter 4 and 2? Let me check. I think so.
I guess my question is more like, would it be before spring break or after spring break that we get it?
It's got to be. When is spring break anyhow?
March 15th.
Yeah. Oh, no, it's got to be. I've got to get it. No, I'll get it out to you. The only question is how deep is chapter 4? We're kind of wrapping up chapter 3 except for the exercises in the back. Mm-hmm. But then there's chapter 4, and I think it does cover 4. So there's problems and variations of problems I can make out of the stuff that's in chapter 4. So, perfect. Yeah, you can get it, not when you have more things, more tools. The problems can be more complicated. Mm-hmm. But my idea of a test is a little bit of calculation, a little calculator, maybe a little Scratch program if you just don't know what to do, and it's kind of exploratory. Mm-hmm. I don't know if this last test was like that.
It absolutely was. And that's part of the reason why, I said when I looked at the test, I'm like, that's a good test. I can't answer these. I had to think about them.
Thank you.
And that's the goal. But yeah, I'm hoping, fingers crossed, that we can have spring break to look at the test.
Yes.
My lucky butt got jury duty for spring break. I got jury duty and it said March 15th. And I'm like, ugh. Okay, I should probably just take that because it's spring break. So I want something to do.
Well, you can actually get out of. I mean, I'm sorry to say that I did this once. I was desperate to get out of it. So I went in front of the judge, and he asked me what I thought of gang members. And like an idiot, I could get fired for this. What I said, Your Honor, membership has its rewards.
Oh my gosh!
So angry. They were so angry, and and that was it. I was excluded from the jury pool.
I'm hoping I get out of it, but I got stuck with literally last spring break. Same thing happened to me. They got me right on the year deadline for when they could ask me to go again. So I'm kind of upset about that, but whatever. I can't.